In this session, we will basically discuss the impulse response function, the idea of impulse response function, how do we apply the concept of impulse response function for the Var model, and what is the condition of identification of the Var model. In order to identify the Var model, we need Cholesky's decomposition. Hence, we will discuss the concept of Cholesky's decomposition. After the analysis of this Cholesky's decomposition, we will discuss the variance decomposition method, and the concept of variance decomposition method will help us to identify the effect of any shock on the endogenous variable of the model, and finally, we will discuss the seam structural Var model and what is the condition of identification of seam structural Var model. Now, let us develop the concept of impulse response function. Now, provided the model is stable, we have seen that vector autoregression can be written as a vector moving average method. Now, if we can express vector moving average method as a function as an alternative to vector autoregression model, then we say that the process is invertible. So, invertibility condition is satisfied provided the model is stable. Thus, in this case what we get a VMA representation of yt and xt, where yt and xt sequence are expressed as current as a function of current and past error. The error in the Var standard form can then be related to the structural Var. That is, error term of the reduced form Var can be related to the structural form Var if this condition is satisfied. Now, in this case yt and xt sequences can be expressed in terms of current and past values of structural error terms. This type of moving average representation is useful to test the interaction between yt and xt sequences through the changes in disturbance term of the structural error term. So, if there occurs any change in the structural error terms, then by considering this impulse response function, we can trace out the effect of the changes in the structural error term on the dependent variable of the model. The changes in error term of yt sequences in the structural equation will have an instantaneous effect on yt, which is known as impact multiplier. So, impact multiplier basically captures the effect of instantaneous changes of the error term of yt in the structural equation of model or structural Var on the current value of the dependent variable yt, and this is known as impact multiplier. However, the changes in the error term of the structural equation of yt will also have the sequence of affecting the future values of xt and yt. Now, impulse response function. The accumulated effect of unit impulses in the error term of the structural equation in yt and or xt can be obtained by taking the appropriate summation of the coefficients, which is known as impulse response function. So, impulse response functions basically trace out the accumulated impact of the changes in the disturbance term of the structural equation of yt and xt. Now, plotting the impulse response function against the time point is a practical way to visually represent the behavior of yt and xt sequences in response to various shocks. Now, consider this function yt is expressed as past yt's and the at is the disturbance term, and from that you can get, if the model is stable, the autoregressive structure can be represented as a VMA structure, and what we get yt is expressed as a function of current and past error, and from that we can trace out the effect of a changes in at on the future yt etc. And if we consider this effect, we get the idea of the impulse response function. So, that is the basically the plots of the effect of the changes in the error term on the past value on the future values of y, that is captured by this coefficient. In a two variable system, you have this, and from that you can generate the reduced form of the model, and where current yt is a function of past yt, and we get the variance covariance matrix, and from that you can get the impulses by assuming the MA representation and accordingly trace out the effect. Now, provided we know the parameters of the structural var, it would be possible to trace out the time path of the error term of the structural model. This will only be possible if the structural model is identified. However, this methodology will not be possible as the structural var is under identified. One possible identification restriction is to Cholesky decomposition such that yt does not have a contemporaneous effect on xt. So, in order to make the model identifiable, what we are assuming that yt does not have any contemporaneous effect on xt. Thus, the changes in error term of yt equation in the structural equation has no direct effect on xt. But since we have incorporated lag values, the lag value of yt affect the current value of xt, and hence there is a indirect effect of xt on effect of yt on xt. But the changes in error term of xt equation in the structural var has contemporaneous effect on both yt and xt. Thus, Cholesky's decomposition forces an important asymmetry in the system. This asymmetry gives us the ordering of the variable. We can define the causally prior variable. A shock to the disturbance term of the xt equation of the structural var affects the error term of the reduced var of both yt and xt, but the shock in the disturbance term of yt equation of the structural var does not affect the error term of the reduced form of yt. Hence, there is an asymmetry. The effect of error term of xt will have both contemporaneous as well as lagged effect, but the effect of the disturbance term of yt will not have any contemporaneous effect on xt. If this is so, then x is said to be causally prior to yt. So, this is a very crucial assumption for making identifiability of the model as captured by Cholesky's decomposition. Now, one can have the reversing of the order and can define Cholesky's decomposition. Cholesky's decomposition by reversing the order and performing the sequence, we can have an identifiable system. Now, we get two type of ordering, one where the contemporaneous effect of yt on xt is ruled out, and other where contemporaneous effect of yt on xt is ruled out. So, how can the researcher decide which of these alternative decomposition is most appropriate? Now, in order to have an answer, we need to consider the nature of the correlation between of the disturbance term. Now, note that importance of the ordering depends on the magnitude of the correlation between the error term of the disturbance, error term of the disturbance term of the reduced form of equation of yt and xt. If the estimated model yields a value of the correlation coefficient to be equal to 0, then ordering of the variable would be immaterial. At the other extreme, if the correlation coefficient is equal to unity, there is a single shock that contemporaneously affect both the variable. If the correlation between the error term of the reduced form equation is significant, then idea is to obtain the impulse response function using a particular ordering. Now, compare the result to the impulse response function using a particular ordering. Now, if the implications are quite different, then that basically implies we need some more additional information in order to make the model identifiable. Now, since unrestricted var are over parameterized, they are not practically useful for short term forecast. However, to understand the forecast error, it is very useful to find out the forecast error at different lags in order to make the relationship more identifiable, more clear. Now, as an example, consider the variance decomposition analysis. Consider two variable yt and xt in a VAS setup. Now, consider the S-step ahead forecast error of yt. Now, denote the variance of S-step ahead forecast error variance of yt plus s as sigma square y s square, this like this. The forecast error variance decompositions error are hence sigma s square y. Now, we can decompose the total change in error variances into two components. One is due to shocks due to x, and similarly we can have a component that arises due to shocks from y. Now, forecast error variance decomposition tells us the proportion of the movement in a sequence due to its own shocks versus shocks to the other variable. So, here we can decompose how much of total variances is explained by the variances of y. Similarly, we can also consider to what extent the variation of total variation is explained by variation of x's. So, if the shocks in the structural equation of xt explain none of the forecast error variance of yt at all forecast horizon, then we can say that yt sequence is exogenous. On the other hand, if yt sequence evolves, in this case yt sequence evolves independently of the error in the structural equation of xt and of xt sequences. So, if we find that variation of xt explain none of the variation of yt at different forecast horizon, then we can say that yt is exogenous. Similarly, if we find that the error term of the structural equation of xt explain all the forecast error variances of the yt sequences, so that yt would be entirely endogenous. So, if xt explain all the forecast error variances of yt at different lags, then we say that yt is entirely endogenous. Variation decomposition contains the same problem as inherent in the impulse response function, and here also we need to assume Cholesky's decomposition. In practice, it is useful to examine the variance decomposition at various forecast horizon, and as n increases, the variation decomposition should converge. Moreover, if the correlation coefficient of the error term of the reduced form of VARs is significantly different from 0, one needs to obtain variance decomposition at different ordering. So, as in the earlier case, if we find the degree of correlation is different from 0, then we have to check the result for different horizon. And impulse response analysis and variance decomposition analysis are taken together is known as innovation accounting. So, by innovation accounting, we basically mean the analysis of impulse response function and variance decomposition. Now, let us consider the problem of identification of the structural VAR model. So, we have seen that it is not possible to identify the structural VAR model. So, VAR model is under identified, and if one parameter in the structural VAR is restricted to the standard VAR is exactly identified, and Sims has suggested a method to identify the system by letting B21 is equal to 0, where B21 is the coefficient of the respective variable. So, B21 implies 0 implies this following setup, and with B21 equal to 0 we get the 9 parameter to solve for 9 equations, and hence all the parameters are identified. And so, B21 implies yt do not have contemporaneous effect on x, that we have already discussed, and this is the basic idea of Cholesky decomposition that we have also discussed. Now, let us consider the example of SIM structural Var model. Now, we have discussed the condition of identification for the 2 variable model, and the condition of identification can easily be generalized for the n variable case. So, consider the example of the SIM structural Var model for the example that SIMs actually consider. SIM uses a 6 variable Var of quarterly data of the period 1948 1 quarter to 1979 3rd quarter. Now, variable includes the real GNP Y, real business fixed investment I, the GNP deflator P, money supply as measured by M1 small m, unemployment U, and the treasury bill R. An unrestricted Var was estimated with 4 lags and each of the variable with a constant term. Now, SIMS estimated 36 impulse response function and put different restriction into the model, and restriction can be tested by likelihood ratio test as we have already discussed earlier. Now, the method of estimation, the result of estimation suggests the following relationship. RT is explained positively by MT, that is the money supply. Money supply is positively explained by GNP, that is GNP has a positive effect on money supply. It is negatively influenced by price, that is negative price has a negative impact on money supply. RT is also has a negative relationship between RT also satisfies the negative relationship between MT, that is there exists a negative relationship between MT and RT. In the GNP equation we get negative relation between RT and YT and positive relation between IT and YT, that is YT is explained positively by IT and negatively by RT. PT is explained by negatively by RT and positively by YT and also negatively by IT, and unemployment rate is negatively influenced by RT, negatively influenced by YT, negatively influenced by PT and also negatively influenced by UT. And ERT, EMT, EYT, EPT, EUT are the disturbance term of the RT equation, MT equation, YT equation, PT equation and UT equation respectively. So, in this case we can find that by putting restriction into the system, SIMS makes the model identifiable and hence empirically estimated the model and also find the following relationship as discussed just now. That is, he got positive relationship between MT and RT, positive relationship between YT, MT, negative relationship between PT and MT and negative relationship between RT and MT. Similarly, there exists negative relationship between YT and RT, positive relationship between YT and IT, positive relationship between YT and PT and also negative relationship between RT and YT. Similarly, unemployment is negatively influenced by rate of interest, negatively influenced by YT, IT, PT and that is all. So, you can get an example where you can use the Var model and estimate the model by suitably allowing for appropriate restriction to the system. In this lecture, we have discussed the idea of impulse response function, the condition under which we will be able to estimate these impulses, the condition of identification of the Var model, that is the idea of Cholesky decomposition, Now, the concept of variance decomposition analysis, and we have also discussed the same structural var model, and as an example we have discussed the case which is considered by SIM, the condition of identification of the model, and what is the actual relation that SIMS has developed from the model.